class because it's going to be about solving some fun problems and trying to play these sorts of games and figuring out, what sort of strategies are there and how we can find such strategies. So, generally, how games, go are like, so this is irritating. I cannot use the pens because of maybe I shouldn't use full screen. Okay. Yeah. So, like, generally, how games go are like they say Alice and Bob are playing a game. Or like you can use any names, but usually people prefer Alice and Bob because A and B. So instead of saying Alice plays this, you can now say A plays this. So just generally for that. Also, Siddharth, you've raised your hand. Do you have something?
My question is, will we actually get to play these games in the class?
Somewhat. We'll definitely have like a discussion where people can suggest moves and then we can
True.
see what moves into you or something like that. We'll figure it out. So yeah, the games go like two players are playing this game where on their move they can make something. They can do something on their move, and then they play alternatively. So like imagine something like chess, right? Like you are allowed to move some pieces, and then the other person is allowed to move some pieces until the game gets over because something happens. So like most of the games in this class won't be nearly as complicated as chess because chess is still a game which, is not solved in the sense that you can't guarantee victory.
Stockfish?
No, Stockfish has not solved chess.
Oh yeah,
Stockfish
it
is
has
only
solved
better than
particular
most
problem.
human beings.
Oh,
Yeah, like, I mean, a human can't realistically beat Stockfish, but that doesn't mean that Stockfish can, for example, guarantee victory against something like there was this Google's Alpha Zero or something. So there can always be better and better
I mean,
computer
it's
things
sold
because
after
chess
like
isn't yet solved. Hmm?
it's sold after like for like when there's
Yeah,
6 or 7
yeah,
pieces remaining.
exactly. That's the table basis kind of things,
oh
right?
yeah,
Like,
7 pieces remaining. It's
yeah,
always solved.
that is true for the end game parts, basically. There you can actually every possible position is solved, but the starting position itself is so complicated and there's so many different things that can happen that it's very hard to solve. But let's take a much simpler example. So something like, let's say there are two piles of stones. Okay, so there are some stones in a pile, like one on top of the other, and then there are some in another pile. And then what you're allowed to do essentially is like choose any one of the piles and erase some number of stones from them. So for example, I can choose the left pile and remove two stones. Then it's my opponent's turn and he can choose a pile and remove, I don't know, three stones. Then it's my turn again and I can choose, I don't know, this pile and remove one stone. And then his turn and he can do this, something like that. And the game goes on. And if you take the last stone, you win. So for example, at the start of the game, one thing I could have done is just get rid of one whole pile. But then the other guy gets rid of the full other pile and he wins. So you don't actually want to get rid of the whole pile.
Okay, so basically, like the move that you can make is you have to choose a pile and you can take any number of stones from that pile.
Yes, yes. So
But
your
then,
move is
sir, the game is very
kind of
easy
to
to
the pile.
predict.
You can just
Uh,
take one stone. You can just take one stone from each pile, like one pile on your first turn, and keep on doing that until if you have to take an even number of stones, then you're gonna win every game.
so okay, let's actually take a few simple examples of what we're saying.
S-
Like there are a lot of stones there. One second, one second, one second. So what are you suggesting? Take exactly one stone from any pile. Was that the suggestion or did I misunderstand?
Yeah, take
So
one
let's say,
stone first.
yeah, okay, let's play. Okay, you play with me. So I'm gonna start and I'll take this turn. What do you do?
From which pile, the 20 or the 23?
Okay, forget the 20 and 23. We're just playing with this 3 and 2 right now. So
Okay,
I took this turn.
which stone? Like I don't
I
see
took
anything
there
right.
were 3 and 2 and then
Oh,
I erased this one.
okay. So then I'm gonna take one stone from the left pile.
Okay, then I take one from here, let's say. And now whatever you do, you lose, right? Because if you take this one,
Oh
I take this
yeah.
one and I win, and so on.
Oh yeah.
So
So
yeah,
maybe you want to
something
take
like
two
that is
first?
working.
Sir, I think I figured out the winning strategy for this type of game.
Okay,
Could I play
so
against you?
sir, also one thing I would like to say is if anyone solves these sort of problems, it's generally good to like wait a bit before giving off the strategy because like it kind of ruins the fun for other people. But at the same time, you can send it to me on chat or something, and I can verify it, and I'll allow you to like give you this thing once we've played enough, right? Something like that is fine. Or just face, yes, I saw your chat, and yes, that's correct. Um, Okay, meanwhile, so let's actually try out, from the very basics. So, for example, if there are exactly one stone in each pile, who wins? Does the first player win or the second player? That's what I'm meaning to say.
The second player.
Second player wins, right? So now let's take, I don't know, 1 comma 2. So there's 1 here and 2 here. Now I could,
Uh,
hmm, now if I take this stone, then I lose if I'm Alice. If I take both of these, again I lose if I'm Alice. But if I take this one, now Bob has to take one stone. Actually, maybe instead of erasing, I should cross out. So Alice takes this one out. And then Bob, now whatever Bob does, let's say takes this one, Alice takes the other one, and Alice wins. So the general idea is like after deleting this first stone, I reduce to 1 comma 1, right? And I know that for 1 comma 1, the first player wins. Also, I'm sorry, I'm not able to see chat of everyone. Siddharth, that is correct. Um, I am not seeing. Yeah, okay. Yeah, it's okay if there's a bit of this thing, and don't worry about this. Okay. Um, and yeah, in general, like it's okay if the class is interactive. Like I don't have any this thing with people talking, but like also that is true that it should be like in a more systematic manner. That's all. Yeah. So okay, 1 comma 2, we realize that this first player wins, correct? Because like I just delete this first one, and now whatever you do, I take the other one. So I think what I'm trying to get at here is that for a lot of these games, it's very useful to take a lot of these sort of base cases where there are very few stones in each. Because, for example, the question I gave is 20 and 23. And when you start with so many stones, it's very hard to concretely imagine what's going on unless you know the answer or you somehow like have some sort of familiarity with these sorts of questions. But if you are on the newer side to this, it's quite hard to concretely imagine what's going on with 23. Okay, I can take 7 stones from here. And there's so many possibilities, right? But when there's only like 1 comma 2 or something, there are very few possibilities, which makes it a lot more convenient for you. And a lot of times the patterns in these questions, these sort of base cases, and how they relate to, bigger these things, they can actually lead you to solutions very fast. So yeah, in general, actually, if you had like 1 comma 10, can someone tell me what's gonna happen? Like 1 stone here and like 10 here. This one's slightly tricky. Any ideas? Also, ideally by people who have not already given me the answer in chat, but um, yes, I'm also not Pranav ideally because I know you know the answer. Yeah, and that is correct. Like basically you pick 9 stones from here because that 10 becomes a 1. And it's the same thing, right? Basically the idea is after my first move, I'm basically the second player. So if I can reduce A comma B to some, I don't know, A dash comma B dash, where I know that A dash comma B dash second player wins. Then A comma B, first player wins. That's the basic idea. And we'll formalize this later with like P and N positions and stuff. But for now, this is like the broad idea that if you have 1 comma 10, I can reduce this to 1 comma 1 and I know that the second player wins there. And I am essentially the second player now because I've just already made my move. So now the second player in the original game is like the first player of this sub game in some sense. So again, Alice wins, right? Um, and okay, what about I don't know, something like 1 comma 1000 also, by the way, you can do the same thing, right? Take 999 stones out. So in general, we've solved 1 comma n because you can just take out n minus 1 stones if n is greater equal to. So all of these Alice wins. What about something like 2 comma 2? What do we do here? This is the question. Anyone wants to play along? Okay, Siddharth, go ahead.
So we know that 1 comma 2 is a first player win. Because we're the second player, you remove one stone from the rightmost or leftmost. It actually doesn't matter.
Right.
Because it will be the same
Symmetric.
thing.
Sure.
And because of the same thing you told, initially you are the second player, but once you remove the stone, it's a new arrangement where you are the first player and you will win this for sure.
Exactly. So the point is, if I remove one stone from here or one from the other pile, now it's 1 comma 2, and I know that the first player right now wins this. So I know that in the original game, the second player would have been winning. That is Bob. But that's not it, right? Because there are multiple possibilities. You can also have deleted both of these. Okay, there also it happens that Bob wins because again he can delete both. So um basically the thing is, if you're playing as the first player, all you need to do is reach one point where the second player wins and you can use that. But if you're the second player, you need to make sure that no matter what the first player does, you are always winning in some sense. So it's in some sense harder to win as a second player, but like not really. What I'm trying to get at is basically you have to take all possibilities. Most of them are very simple here. Like this one was very simple that you just take out the other ones and second player wins. And here also you take out, like you reach 1 comma 2, the first player in this position is winning, which was the second player in the original position. So no matter how Alice made his first move, her first move rather, Bob would win. Okay. That's cool. And similarly, now if we have something like 2 comma 5, we can always take out. Okay, someone wants to answer this. What will we do for 2 comma 5? Go ahead, Siddharth.
2 comma 5 is a first player win. Remove 3 stones from the rightmost pile.
Right, exactly.
Making
So,
this a second player win.
yes, exactly. Now you're going to basically reduce to this 2 comma 2. And then you're going to, again, copy in some, or whatever.
This
I
can
kind of
be
gave away an
generalized
idea.
though.
Yes, exactly what we're going to do now. So we've kind of got somewhere, right? We've got that 1 comma big Alice wins, but 1 comma 1 Bob wins. And so actually, let's just see all the places where Bob wins as of now. So 1 comma 1 Bob is winning and 2 comma 2 Bob is winning. But actually, those are the only things till now where we've seen Bob winning. And like the basic guess that you need to, and these are usually the harder parts of the problem because you start seeing some patterns, but you also have to have the confidence in yourself that these patterns should generalize. And usually they only come after you've solved the problem. In fact, you won't really be sure that what you're saying is correct unless you're done with the problem. So the guess is that n comma n is the only time Bob wins. And like one part of this is easy because if you start at like n comma n plus 5, and I know that n comma n Bob wins, then I can remove 5 stones and the first player will win. If that makes sense. Basically, on my first move, I'll remove 5 stones. And now I'm the second player in something I know to be winning for Bob. So I could use that. But the question is, why should n comma n in the first place be winning for Bob? And that's kind of the main point of the problem. Yeah, I think okay, someone else. Yes. Kian, what you're saying is also correct. And okay, but like yes, I think there are a lot of ways of actually going about why n comma n wins for the second player. I think one of them is like a straightforward sort of induction sort of argument, which is like if I reduce n comma n to, I don't know, like n comma, let's take an example rather, like n comma 10, right? And I don't know, I remove 6 stones from here. So I go to 10 comma 4. And now I want to show that the second player in the original thing can win. So whoever was Bob over here, they can win now. And that person is now Alice, right? Because like they are now the person who needs to make a move. And that's equivalent to 10, 4 being winning for the first player. But that we can show by removing 6 stones here and making it 4, 4. Because by some sort of induction, because if we had assumed that 1, 1, 2, 2, 3, 3, all the way till n minus 1, n minus 1, these points pay, Bob is winning. Then we can show that n, n also Bob will be winning. Because now whichever you go to, I kind of link it to that sort of position. But it's still a bit messy. So what I want is a very concrete way of writing this up, right? Can someone give me a concrete way to explain this strategy to someone?
So can I say?
Go ahead.
So you want to do a generalized problem, bro?
Mm-hmm.
Yeah. So suppose we start with the pile of x comma y.
Yeah, right now I'm just trying to prove that x comma x or n comma n whatever will be winning for second. And that would imply that x comma x plus y is winning for first. So, yeah, let's just try proving this. Do you have something for
Yeah.
this?
So
Hmm.
yeah. So in the first one, if n comma n, if the pile is n comma n, then the Alice will take out some number x. So we'll have
Yes.
n minus x, and then we know that if it is Alice's or Bob's turn, if it's your turn and you end with 1 comma 1, then you will lose because
Yes.
you'll have to take one stone and then the other one will take the last stone and win.
Hmm.
Bob will win. So, and if the pile is 2 comma 2, then
That
Bob
also we've seen. Bob wins.
can take
Sure.
one stone and then Alice will have to take another stone. Yeah. And
Yeah.
for 3 comma 3, Bob can take, no, Alice will have to take 1 or 2 stones and then Bob will take as many stones as she took, and then Alice will again be
Exactly.
left with 1
Yeah.
comma 1.
So the general idea of what you're
Yeah,
getting
so
at
with
is
the
that,
help of induction, n comma n will always be winning for Bob.
yeah,
Because
like the general idea is that if you take out x turns from here, I'm going to take out x from the other one, and I'm going to get back at a point where both things are equal. And
yeah,
once both things are equal, I can, either use induction or I can even like just straightforwardly say it, right? Because
yeah,
like if they're always equal at the end of your term, then that means that if the answer is ever 0 comma, or rather if it's ever like what makes the person win, right? The only time you can force a win on your turn is if it's a comma 0 with a greater than 1. And that's never going to happen at the end of your turn, because at the end of your turn you can only read 0 comma 0.
yeah.
That's a bit of a vague argument, but yeah, like the general idea is this only, right? You take 5 from
Okay,
here, I take 5 from here. So when one pile gets over, the other pile gets over.
okay.
So
So,
I am the one who took the Bob is the one who took the last one.
yeah, so in the other case where it is n comma n plus x,
Yeah,
then
that's
Alice
easy.
can start with taking x stones from the n plus x pile, so there'll be n comma n. So
Hmm.
we know that whoever's turn it is in such a position where two piles have same number of stones, they'll lose. So it is Bob's turn, then he will end up losing, and so
Hmm.
Alice will win in this n comma n plus x.
Sure.
So that's
So
the
what you've
generalized
got
strategy.
is that Bob wins if and only if the two number of piles have the two piles have equal number of stones. And here, for example, we had 20 and 23, so they were not equal. So in fact, what you would do is take out 3 stones from here. So this becomes 20, 20. And now
And
whatever
eventually
Bob
Alice
does,
will
you
win.
copy.
Bob will lose and Alice will win.
Yes. So I think one of the key points here is that the fact that someone has to win, that itself is something that takes some digesting, like you're given any random problem, and there's a theorem actually, which is called Zermelo's theorem. I'm just going to state a slightly weaker sort of version of it, which is basically saying that if you have any sort of decent game, which is like game has to end, um, and no element of luck, these sorts of basic things, right? It can't be a card game where, it depends on whether you got lucky or something. Like something like chess or tic-tac-toe or um I don't know, those sorts of, not hand cricket where you're playing a random number and it depends on something like that. So if you have this sort of game, for example, this game was also something like that, and players play alternately or something. I
What
don't know
about
how
real cricket?
real cricket also has a lot of element of luck, and I mean, I wouldn't call it luck, but like it's definitely not very comparable to a mathematical game because at the very least there are factors like wind. So like whether the ball this thing or like I mean it's I wouldn't actually compare any outdoor game to the things we're doing here. These are more like you can compare to something like a board game or a indoor sort of game because in general like yeah, I just don't know how you would connect something like cricket here. It's an interesting question though, and it's definitely something worth thinking about. But I don't think you can solve cricket mathematically because it has a lot of element of, your personal, uh, yeah, and it has element of luck and also like humans can't perfectly like time everything. For example, like our vision, you only see something every 1/10 of a second or something. You don't have perfect information for that matter. So another thing here is like you have perfect information, something like that. Anyway, the point is that any such game has what we would call a winning strategy for one of the players. So, or there's also a drawing thing for because like games like cricket, games like chess, I mean chess and tic-tac-toe, they also have draws, right? But if you consider games which don't have draws, then what this theorem basically says is that either the first player has a winning strategy or the second player has a winning strategy. One of them must happen. So it's not possible that neither player has a winning strategy. And for example, here we had that, second player always has a winning strategy when it's in command. Yeah, Swasti, go ahead.
Yeah, is there like a proof for this theorem?
Sorry?
Is there a proof for this theorem?
Yes, yes. We'll actually talk about this proof. We can either do it straight away or we can do it after. I think it's better to do it after a bit because we'll also actually discuss something which is related to the proof and then we can actually see it a lot more easily. And there's also very fancy, proof of this using some logic kind of things. So we might see that also but I don't really fully understand it. So it's like it's actually very weird. It's like something like saying there exists and for all other something like that. I will come to it and we'll definitely talk about it because I believe that if you learn any theorem without a proof, it's kind of sad. Like especially when it has a fairly elementary-ish proof, which this theorem does have. And actually, the more general form of this theorem says that if you have draws also, then either the first player has a winning strategy or the second player has a winning strategy, or both of them have a drawing strategy. So both of them can force a draw. So yeah, and one of those three things has to happen. But yeah, I mean that's more of the game theory part, which I was actually talking about at the very start. That how this might be a little different from game theory. This is more about fun problems which are like if you have a computer at your hands, most of these are like instantly solvable by the way, because like computer can just bash through all possibilities, find out patterns, and then like there are actually things called Grundy numbers and stuff, which are like made for computers to be able to solve all of these sorts of games. But we won't get into that right now. Maybe at the end we can talk about that. Let's talk about another question. I think one of the things that we didn't really actually there's a quote from Pranav Shriram, so an Olympiad Combi book. It says that they said uh, no cheating because like the general rule for these math games is like you can't cheat, like you can't subtract from both piles on your turn, something like that. But they said no cheating, but you can still copy. Because like the whole strategy above was that you're kind of copying the other person. If he takes out 5 stones, you can take out 5 stones. And if he takes out three, you take out three. And that's actually a really useful thing in combi games to use this sort of symmetry, which is like um comes up a lot. In fact, it'll come up in the problem we are just about to do now. Um, yeah, so this is our next problem. Basically, it's like you have like a square table. I can actually replace it by a circle, rectangle, but anyway. And you have some, and okay, 1 square meter. I don't really care. Some side lengths and 1 centimeter diameter circle. So you're basically placing like circles on this board, again and again, and alternatively. So Alice plays one, then you play one, then you play one. And obviously, like it's a very big board, so you can do this for a lot of time. But eventually, what happens is like it's really really crowded. Like everywhere there's a coin, and now wherever you try to place a coin, there's just no area for it to fit because the rule is that you can't place it on top of a coin. Like it can't actually overlap with any coin that's already placed. So you can't do something like this. It has to be like completely non-overlapping. It can touch, but it can't overlap. Actually, I mean, even touch you can disallow. It's like doesn't really affect the solution. But yeah, and like the question is, who has the winning strategy? Yeah, one of Alice or Bob has the winning strategy. Uh, we have to find out who. That's the main thing. Some yeah, I've got one answer. So that have you proven it or is that your guess?
I think I might have gotten a proof, but
Okay.
at the moment it's a guess.
Mm-hmm. So let's actually discuss it, right? I think we can directly discuss. Like I've kind of given away the idea, which is to sort of copy and use symmetry. So
Oh yeah,
you
that was my idea.
yeah. So what are you trying to do around that exactly?
Like my idea was kind of like mirroring around the
Uh-huh.
diagonal.
Uh-huh. So yeah. So like that's a good idea. You have this sort of diagonal. Also, why not do something like this for? Okay, let's just use diagonal now that you mentioned it.
Or you can do it vertical around the symmetry.
Yeah. So like the point is like he plays here, you play here, and if he can make a move, you can make a move. But the issue is what if I play on the diagonal?
Oh
Like
yeah.
you can't copy something which is on top of it, right? That's an issue. So that's actually the main point of the problem. Otherwise, it's absolutely trivial.
Can't you make another line of symmetry
Mm-hmm.
from the top left? Yeah, by like that, and you just put the other
Yeah. So you're
coin
saying
on the
now
opposite
play
side.
over here, correct?
Yeah.
Yeah. So if it's on the diagonal, you would reflect about this. Okay, some sort of accepting thing. Actually, what you could do, a neater way of saying this is just reflect about center. So either way, you can just reflect about center. But anyway, the question I have is, what if I play at the center? Now we're stuck, huh?
If you play at the center.
Now there's no reasonable way to copy. How do you copy something that's on the center? Oh, so sorry, chat messages. That is what you use to win. Uh-huh.
Sir, I have an idea.
I see you, Omsi. I see you.
Sir,
Um,
I think we should play another random move and then it's the other player has to copy our moves. I think so. I'm not sure.
I don't understand. Who has to play the random move?
No. Now, if someone plays on the center, then we can just play somewhere else, completely random.
Right.
Now, the
So
other
the
player has to
issue
copy
is
our
like,
moves.
yeah, so like what we were saying is, you play somewhere, Bob copies, so Bob wins. But the issue with that was Alice plays at the center. So let's say if Alice plays at the center, Bob plays at some random point. But the issue is, Alice copies now.
So what do we have
So,
to do?
So
so the answer is
every
actually Alice wins. Like Alice plays at the center and then just copies whatever Bob does. Because the only way we would have run into an issue was if you played at the center. So I just played at the center at the start, and now there is no issue. So now whatever you play, I can copy you. So it's actually very sad because like Bob came up with the whole strategy, I'm going to copy you, I'm going to do this, I'm going to do that. And then Alice just heard his entire strategy and used it against him. So life in
So it's
combinatorial games.
Alice winning.
Yes, Alice wins.
Yeah.
Oh
Um,
yeah, center strategy. Here we come.
Exactly. So you play at the center, and in fact, this works for like if you had a circle also, because again, you can reflect about center. Even for a rectangle, you can for that matter. So, yeah, in general, the idea is like you play at the center of whatever shape it is. Like it can't be for a random shape also, because then you won't have symmetry. But for like some basic ones, it's fine. Um, yeah, that's sort of cheating. That's the thing, right? But
I
you
know.
can copy the strategy. That's what I said.
They
You
said
can't
no
cheat.
cheating, but you can copy.
Exactly. So yeah, it's copying, but not just copying the moves, but also just copying the strategy.
Bob made this entire strategy, and
Yeah,
Alice just steals
Bob
it.
thought it's so smart because he came up with all of this, but then
Yeah,
Alice
but then
used
Alice just put in one coin in the center and his whole strategy of Bob is ruined.
And
exactly.
it's used against him that too.
Yeah, it's not even just ruined, it's like used against him. That's so sad. Okay. Let's do another problem, I think, of a similar flavor. Yeah.
Hmm.
And now finally, okay, Bella and James. We can imagine Alice and Bob. Like I just took it from some contest where they, eventually people get bored of Alice and Bob, and then
Yeah,
you think of
finally different people here.
yeah, like I mean, Indian contests have also have like
Vikram and
Vikram and
Betal.
Betal. I think once we had, and then once we had like Calvin and Hobbes. So yeah, and like in fact, some class I think Atul took, he put like Pranjal and Rohan. So you can make whatever names you want. In fact, that makes problems your own, and you can give them flavor text. That's fine. Okay, the problem. You have like a circle, and you have some points. Okay, let's say there are 5, 6, 7, 8 points, right? And okay, mix. Let's say 7 because of pointless. Okay, 7. And what you're allowed to do is make a triangle using 3 unused points. Okay, so I make a triangle. And now all of these 3 points are used. But the issue is now whatever triangle, I can't create this triangle because it intersects with that triangle. So the only triangle I can create now is this one actually. Like I can't, basically it has to be either on this side or it has to be on this side. I can't overlap with the triangle that has already been created. And again, the question is who wins?
I think that it depends on how many points there are
Yeah,
initially
yeah.
starting.
So like the
I mean, here the
question
first player
is
wins, right?
more will be like, sorry?
The first player wins, right?
No, the
Um,
first or the second player can win.
Yeah, I think it's like if there's an even number of points, it's
I
a
mean,
second
The
player
second
in
win.
this
player.
Other
case, if you
Yeah.
take
okay,
the
let's
3 in the
actually solve
center, right?
7, right? Let's just solve 7. What is happening for 7? Who wins for 7?
The
first
first
I think.
ones.
First player.
Yeah,
Oh,
the center, because they make a triangle in the center, right?
Our sir is
like
playing a
this?
joke on us, and it's a second player.
Yeah, I mean,
Yeah,
yeah.
like now the issue is I can't actually make any triangle. Like the
So
for you
basically,
to be able
first
to
second player loses.
for 7. For 7, we've got that first player
Yep.
wins. The sale wins. Okay. Yeah, but the question is how do we do this for like bigger? Like someone suggested odd even or something.
Let's do like 8.
Let's do lots, right? Like some big number. I don't even
Okay.
know how many these are. You'll have to count. Okay,
1,
1,
2,
2,
3,
3,
4,
4,
5,
5,
6,
6, 7,
7,
8,
8,
9, 10,
9,
11,
10.
12. Where did I start? I'll have to count
Sir,
again.
I understood.
You think you understood? Okay, you can
Yeah,
maybe try and wait, don't give away the strategy if you're sure you know the answer, but you can write it on chat and then you can explain the solution once people are ready for it.
Okay, wow, this is that problem, right? Which wasn't like so quickly set as that.
Yes,
This
it
is like
was
amazing.
it's good.
I wonder
Okay,
what to do.
maybe 13 is too big. Like it's hard to
Oh,
actually
Or
imagine.
too
Let's
small. We
wait,
need to
wait.
add one
What
more
if
dot.
okay,
what
wait.
if the What if the first player makes the largest triangle possible?
Yeah,
Largest
Like,
triangle.
And
if I
then-
connect point,
Then there's
Something
like
like 1,
only
5,
three.
10 or something like that
yeah,
kind of
and
thing,
then
right?
like
Like
split,
which is
split,
almost
split,
equilateral.
and then like repeatedly like split the other regions and then just
So, but
kind of.
the issue is once you make your move, now you cannot control what the other player does, right? Like he can cause all sorts of havoc for you. So, okay, actually, let's solve it for smaller numbers just to get a brief idea of whether when is Bob winning, if at all. So, for example, 3 we know A wins because he just makes a triangle. 4 also A wins because again he makes 5 also A wins because once he joins 3, there are only 2 points left, so you can't make a triangle. 6
Oh,
wins.
Bob, I think.
Yeah,
That's
Bob
it.
only.
Are you sure?
No, wait.
Nah, if he
Oh
makes like
no,
in the
no.
center.
Oh yeah, Alice wins.
it
Alice
depends
wins.
on what type of triangle he makes.
Yeah, but
But
that's the point, right? Alice has the freedom to make whatever triangle he likes.
yeah,
So
because we are
he's
Alice.
gonna
Yeah.
make the triangle that makes himself win. So yeah, 6 also A wins because he can like split it so that each of these has at most 1 in them. So
7
so
A wins.
7 we got A wins. In fact,
if
what I'm
n
go ahead.
so what if n was any multiple of 3, then only the second person has a chance to win.
Is
Yeah,
that true?
I
6
think
Because
A
even
maybe.
wins.
6, even 3 and 6 A is winning, right?
Yeah.
I don't
Yeah, but maybe that's true. Like maybe only ones where he wins is like some big multiples of 3. We don't know. Let's see. So like for example, let's take how much is this? 3, 6, 9, 12, right? Like basically if you take any number less than 12, no, less than 9, less equal 9. Like if I take 9 for example, what I could do is like make the biggest equilateral triangle or something, which is like this one. And the point is now each thing will have like 2 things on their thing. So no triangles are left, some sense. So till there, it's like very easy to say A wins all of these. Is this clear to people, by the way?
Yes, but
Like,
then 10 B wins if we do
yeah,
this.
yes. So if you, are you sure though? Like, the thing is for 10, you don't have to make a big triangle anymore. You can do whatever you want.
Sir,
Oh, yeah.
I didn't understand how come 6 Alice once again. Can you please
Yeah,
explain?
for 6, we have these 6 points, right? You make this triangle.
Yeah, you make a triangle.
Yeah, and there are 3 points which are like on different arcs. And now he can't make any triangle. Like he can try to make this, but it overlaps, right? You're not allowed to have overlaps.
Oh,
So
okay.
And
if
you're
you were
not
allowed
allowed
to
to
have
go
overlaps,
outside.
then you can just what?
Are you allowed to go outside the circle?
Can you tell me which triangle with points inside will have a line outside?
Oh, yes. Oh, it's supposed to be points inside. Oh, now I get it.
It's on the circle. These points are on the circle and you're joining. Like
Rushil, do you know
points are
what's
already defined and you're just joining them. Okay, but question is now 10, what happens? 1, 2, 3,
10 I
6.
can prove B wins.
That's very bold because I think A wins.
Okay, now I'm not sure anymore.
But what is your idea?
My idea is kind of like this. Use the same technique that we used earlier.
Okay.
Alice forms a triangle.
Sure.
7 remaining dots and oh yeah, it doesn't. Oh yeah, it doesn't have to be on one side. Oh yeah.
Yeah.
Yeah, I think A
I'll
wins.
give you, in fact, I'm going to make this triangle. And the issue is now there is this triangle, but there's also this triangle. So like you make one of them, I make the other one, and I run you out of points. And yeah, this is a lot trickier than it looks actually. Is this clear to people, by the way? Like you're basically making this triangle, and now yes, this triangle is ready for Bob to make, but this triangle is also ready. So if he makes one of them, you make the other one, and now there is no move because you can't use this point and there's no other point left. So yeah, the question is like, how do you do something like this in general? So we got 10 also even. So like at this point, like it feels like a safe guess that okay, it's not a safe guess at all, but it's a guess that Bob just never wins. Also, Shit is just saying something. Odd multiple of three, it depends on the number of points we leave for the other person, right? Yeah, so that's the thing, right? Alex has a lot of options on their first move. If they don't play well, the second player can win. But they will try to play in a way that the second player can't win. So on your first move, you have a lot of freedom to do whatever you want. But as soon as your first move is done, you lose that freedom because the second player can do whatever they like. So, like, this is assuming that we're trying to prove that the first player is winning. It may not even be that, but it's a good guess because we've gone through 10 cases and none of them Bob has won. So, uh, yeah, can I say?
Rushil, do you know what's so funny about this problem?
What's so
I
funny?
actually solved this in Microsoft Whiteboard.
Nice. See, it's not that bad, is it? It helped you solve the problem at least. Okay, but people, let's come back to this. Yeah, so can someone tell me like why this sort of thing worked? What exactly did we achieve here? We basically on our first move we created a triangle which like makes it very hard for him to do anything because whatever he can if he can do something, we can do something. Do you see the symmetric arguments coming back?
Yeah.
Like you're basically trying to split the set of points into two sets of points, and now whatever you do on one set of points, I do on the other set of points. That's going to
Again,
be
we
our
are going to copy only. Again, we're going to
yes,
copy.
exactly. So Alice on their first move, he basically in some way splits them into two sets of equal things, and so that this point, this place is useless. It has like one stone or something, 1 point or something. So you can't use this one at all. And now what all is left is like some, I don't know, 5 points here and 5 points here. So if he makes some triangle over here, I can make some triangle over here. And if he runs out of triangles over here, then he lost. So yeah, something like that here. What can we do here? We want 13 points, right? So you want to split it into two equal parts, and you're going to have used up 3 or 4. So in fact, actually what we can do is we can leave 5 points on each. So you'll leave 5 here, and make a triangle of like these two are consecutive. And this is, so just to put this into things, I'll give the, so you join one, wait, did I count correctly? Yeah, 1, 7, and 8. And that's the whole magic about this, right? Now there are 5 points left here, and there are 5 points left here. So whatever he does on the left half of the board, you can do on the right half. And again, you can copy. So the question just becomes, how you can make this sort of starting triangle in an accurate enough way. And there you have to like be careful about some parity and odd evens type of things. But that actually is something I'll leave to you for you to find the finish. But that's actually the broad idea here that you make your first move so that um, there are now two sub games, and both of those sub games are identical. And this is a common idea, right? Because even in our first thing, we basically had two games going on simultaneously, and you choose either one of the games on either turn, and whatever I remove from this, you remove from that. It's see the exactly same thing. You're making a triangle here, I'm making a triangle there. You're making a triangle here, I'm making a triangle there. It's like the same idea, just in a completely different sort of problem. Which is why these sorts of problems are fun. Like when you see this problem, you won't actually think of the first one we did, but after you solve it, you'll feel they were so similar in some sense. N minus 3 by 2 should equal an integer. Yes. But then the question is how come like basically n minus 3 by 2, if it's an integer, then you can do this, right? Because you can make 3 points and have equal. But the question is, what do you do if it's even? And that's why we solved 10, right? So think about 10. We had a point here. That's your for that. Um, okay. So yeah, if also someone raise that. Yes, go ahead. Yeah. Okay, I think maybe they raised it by mistake. Kian, do you have something to say?
No.
Okay, can lower your hand or something, I guess. Yeah. Let's see another question. Okay, so I think we've seen a fair few of these copying strategy kind of games, but the major issue with these strategies is like they don't always work. So like for the simpler sort of games, yes, they end up working quite often and they work really well and they work really fast. So like you can be done with the problem in minutes if you just think of the right sort of way to copy. But at the same time, there may not be a copying strategy. For example, like you try to copy in chess, it's like really bad, right? Like you lose your queen or something because you try to copy a queen move, you'll just capture your queen and then you can't move your
You
queen because
can't
it's
copy
captured.
that though.
I mean, in chess, somewhat you can copy the first few moves, right? He plays d4, you play d5, he plays
I
c4,
mean, you can. I mean, you can copy the first few moves, but after your queen's taken, you can't copy. You can't just magically make their queen vanish.
Yes, exactly. Like if your queen gets captured by their queen, you can't capture their queen with your queen because it's already gone. So yeah, like the idea I'm trying to illustrate is like, um, yeah, we're doing that, but not just now. If I to answer your question, um, at some point we'll do that problem. What I'm trying to get at over here is the concept of P and N positions. So this is actually somewhat similar to what we've been doing till now, but we're just going to try and formalize a bit, and then we'll actually use this to prove Zermelo's theorem as well, which was that games do have winning strategies. And basically, what this says is that I'm going to assign like you have your A comma B for the that game, right? You have lots of possibilities. I'm going to assign each of these either P or N. When basically A comma B is P if A wins and N if B wins. So it's essentially the same thing, but it's a little more systematic way of thinking about it, I feel. Especially because you don't have to convince yourself that okay, whoever was Alice is now Bob now, but Bob is Alice now. And it's very confusing like that. But this is a slightly more easy way to think about things. Basically, what A comma B is P will mean is that whoever is about to play now, um, wait, let me just think again. Yeah. Okay. A comma B is P if whoever is about to play now wins. So if let's write that if whoever is about to play now has the winning strategy. And it's N if they don't. So if the other person has a winning strategy. If whoever is about to play does not. Okay. And yeah, it's essentially the same thing. So how you would frame your original thing in terms of this is like, okay, first of all, why is this useful? I think one of the main things is like basically if you start at an A comma B, and I'm taking that example, we'll see more examples as to how it comes up. You basically a lot of possibilities. And we are yet to find out whether this is P or N. But we know that for each of the possibilities that this leads to, whether the answer was P or N, because we've already solved those. Like we're coming from very basic ones to the harder ones. So in some sense, we would have already done all of these. Yeah, Kian, go ahead.
So can you repeat the question to me? I did not get it. Sorry.
Yeah, we've not actually gone to any question as of now. Like we're just talking about this general idea of using P and N positions, which is basically that if you have a certain state in your game, that is your game is in like your original thing, right? There were a lot of possible states for it. It could have been at 5 comma 8. It could also have been 1 comma 1, the number of stones that is. And in general, it could have been A comma B, right? And uh from A comma B, you can go to, I don't know, A comma B minus 1, A comma B minus 2, you can go to A minus 1 comma B. But the point is all of these are solved. So like you can, instead of actually writing the thing, you can just write P, P, N, P, not non-deterministic polynomial time. But yes, like basically all of these things below are solved. So the question is, what do you need to look for in these things? The thing is, if you find an N below you, that means that this is going to be P. Because if this is N, that means that the second player over here wins. And that is the first player over here. So essentially, if I can find any n below me, I'll go to that and I'll use that to win. So if there's any n below me at all, then this thing is P. But everything below me is P, then this thing is N. Because no matter what I do, the guy after me will win. So in general, for something like 2, 2 being n, what you would see is your possibilities are 1, 2, 0, 2, 2, 1, 2, 0. And you know this to be P because first player wins here. This also to be P, this also to be P, this also to be P. So this ends up being N. So the second player wins here. So I think it's just a fairly useful way to think about things. And also P and N, I'll just tell you what the meaning is. Like it's player and next player. It's a very weird sort of thing, but it's quite it's used in a lot of places. So like I wouldn't question it too much. But yeah, like I mean, you're free to call them X and Y if you like. It's just the person reading your solution might end up having a tough time because they're too used to seeing P and N somewhere, and X and Y is harder to get used to. Go ahead. Yeah.
Yeah, so if A is equal to B, then it is N, because the whoever is playing doesn't have cannot be is not able to
Yes.
win.
Yes.
And then
yes.
but if A is not equal to B, so either if A is greater than B or less than B, then it is P, because who is about to play has a winning strategy.
Exactly. Like if you have 3, 2, then one of your possibilities is 2, 2, which you know to be N. So if you have a N below you, then this is P. And that's we have an N below us, so we have a P.
Yeah.
Yeah. So let's actually just make this more clear with an actual problem. I mean, some of you might have seen this, by the way. This is a very fun common game which is actually played in like truth and dare situations where like you need to decide who is the next guy who will have to answer the truth or dare. And what you do is like each person either says 1 or 1, 2 or 1, 2, 3, and then the next person has to either add 1 to it or add 2 to it or add 3 to it. So like the game can go on something like I say 1 and the other person says 2, 3, and I say 4, 5, 6. Then they say 7,
So
and
I
I say
know
8,
this.
9.
I know
Yeah,
this.
exactly. It's like quite well known. And basically the point is if I say 21 or any number greater equal 21, I lose. So I
So
need to win.
I know this game.
I think I have a winning strategy for player 1.
Exactly. For player 1,
If you just can I say it?
okay, play with me. Let's
I
see.
am
You go
sure that
ahead.
player
I'll
one
try.
will
Okay.
Let's see if you can beat me
Okay.
with player
player
1.
one will win.
Okay, I'll go first. 1.
1. I'll say 2, 3, 4.
Okay. 5.
5, 6, 7, 8,
9.
10, 11, 12.
I'm
Huh?
sorry,
11,
the
12?
second player will win.
10.
I'm
I'll say
sorry.
10,
13.
11, 12. 14, 15, 16.
Hmm. 7. Okay. I'll do
You this game.
17. I'll do 17.
19, 20. And then you have to say 21. So you
Oh.
lose.
Oh, damn.
So yeah, I think I kind of gave away the idea also, and a lot of you probably know this, so I won't like keep you hanging on this too long. Like the idea is basically that I'm going to keep going to multiples of 4. So like if you say 1, 2, I'm going to say 3, 4. If you say 5, I'll say 6, 7, 8. If you say 9, 10, 11, I'll say 12. So I'm going to basically make sure that at the end of my turn, it's a multiple of 4. And that means that on my turn, it'll become 12 and 16 and then 20. And then he'll have to say 21. And then he'll lose. So, yeah, the second player wins. But what I'm looking here is not for a, solve the game, but more about if we didn't know anything about this strategy, how would we have gone about solving this problem? And that is using this P and N positions, it actually makes it a lot more convenient. So for example, we know that 20, is it a P position or an N position?
It's a N position, because whatever you say, you'll have to say 21 and you lose.
Right. Yes. that is
Yeah.
true. What about 19?
It is a P because you can say 20 and the other one has to say 21.
Yes. So the point is, if you have 19, now your options are 20, 21, 22. And 20 you know to be n. So you know that whenever there's an n below, then this becomes p because you can go to it and make the other person suffer. So similarly, 18 also you have an option to go to 20. So
Also
again, it becomes
17 you
p.
can go to 20.
Exactly. 17 also you can go to 20. So
Yeah,
all of
but
these
for
are p.
17, but for 16 you'll have to go either to 17, 18 or 19. All are P, so 16 is N.
Exactly.
Or
So
15,
that's how
15
we
is
can keep reducing. So
15 is
16
coming
and
to 13 because they can take you to 16. They are P. And
yeah.
due
So,
to the induction, we can continue this till 1.
mhm. Yeah,
So
exactly.
we can prove that 1 is P. So whoever starts
Actually, what we're
first,
looking at is 0 because like the game has started at 0 and now you're going to add
so
1, add 2, add 3. And 0 is n position. So is the second
yeah,
player.
so whoever starts in this game loses.
Exactly. So yeah, just to make this more clear, like the point was that we're basically starting at a case which is very, very simple. Like 20, we just know what is going to happen. And then we're using this to like build downwards onto like finally we reach like 1 and 0, which are actually quite confusing, but because we have solved everything before it, it's actually very easy. So, why this is really useful is like, I don't know, if instead of like giving you 1, 2, 3, and 21, if I give you 1, 2, 3, 4, 5, 6, and I give you 162. Now, it's like,
Can I solve
hmm,
this?
sure,
So 1/6. Wait,
I'll have to do this myself, by the way. I don't
no.
think. Yeah, whoever says 162 loses,
I,
right?
yeah. So
Greater
161.
equal than.
I know the formula for generalized problem. If you subtract 161 from 160, so we have 161, and then there are 7. The next 7 ones are P. So
Next 7 or next 6.
oh yeah, the next 6. So if 161 is divisible by 7, then
161 is in fact divisible by 7. That's lucky for
yeah,
you.
so then the whoever starts loses.
Exactly. So yeah, what we're going to get at basically is 161 is n. So the next 6 are going to be p because what you
Yeah.
can do is you can
And
go to
then,
161 for each of
yeah,
them.
so for all numbers that are divisible by 7 are going to be n only. So since 0 is
Yes.
divisible by 7, then
Yeah.
since 0 is divisible by 7, it is going to be n. So whoever starts this game loses.
Cool. Yeah, and I think in general, if you have 1, 2, 3, 4, 5, 6, you actually have to just look at the multiples of n plus 1 and like if it was a multiple
This
of
is a
n plus
generalized
1, then
problem.
yeah, if you have like this is
1, 2, 3, 4,
n,
5, 6 till n,
then
and
basically
then
you need to check if n minus 1 is
yeah,
divisible by n plus 1. If it is,
yeah,
then second player
uh,
wins. If not, then first. But okay,
yeah.
I'm going to make it even harder for you. What if I give you that only moves you're allowed to do is something like 1, 2, 4, 6? And now it's going to be really messy. So I'm not actually going to solve this, but the idea is that you can still do the same thing because, like, if I don't know, if you have to see 100, then I know 99 is an n position. So I can say 98, 97, 95, and 80, no, 93. All of
I've
these
seen
are
a problem
definitely p
similar to
positions.
this.
Mm-hmm. Yeah, like I'm not actually going to solve this, but like the point is these ones are definitely P. And then 96, all your options go to N positions or something like that. Like basically you can keep doing this, it won't be as nice. But A, for a computer, it's really nice. So a computer can do this in a matter of seconds. And B, of like you can actually prove that there will in fact still be a pattern modulo some number. Like for all numbers divisible by some number, the thing wins, or something like that. Or like which have some
Well,
remainder when divided by
then we
something.
can go to a generalized problem where we can see only numbers a1, a2, a3 up till an,
Yes,
and then
yes.
there's the number. If we say capital N, then we lose.
Yeah. That's the generalized problem, and it's not doesn't have a very nice, decent looking answer, but it is doable to solve for any. You give me anything, I will know how to solve it. It'll just take a bit of effort. So, actually, we'll take another question now, and that is similar to this thing, but now what you're allowed to do is you're allowed to delete from an infinite set, which is like powers of a number, particular. I'll show you the problem. Yeah. So yeah, the question it's framed a bit differently, but it's sort of the similar sort of problem. Like you start with n, and what you're allowed to do is you're allowed to subtract a power of k. So you can subtract k to this, like let's just say k is 3 for simplicity. We'll solve it for all k later on, but let's say k is 3. Then what you're allowed to do is you can subtract 1, you can subtract 3, you can also subtract 9, you can also subtract 27, you can also subtract 81, blah blah blah. But you can't also make the number negative, by the way. So if your n is like 40, then you can't subtract 81. You can subtract 27, 9, 3, or 1. And then the other person goes and makes a turn, and you go. And then,
Okay.
like, basically, whoever reaches 0 wins, because
Yeah.
then a player
Okay.
cannot make the next turn. Yeah, go ahead.
I'm not actually sure about the solution, but I think that suppose we have must if a number can be expressed in every number must be expressed in the as a sum of
Yes.
k
In base
k
3, you're
a1
saying, right?
plus k raised to a2 into k raised to a3 and so on. So like
Sure.
we can have suppose we have the number 3. 3 can be expressed as 3 or 4
Yeah,
can be
like in general, you can express the number in base 3 somewhat like this, with like zeros, ones, and twos.
yeah.
That's what you're getting at. Like
Yes.
basically, this would mean like 3 raised to some whatever this is, 3, 5, 7, 9. So 3 raised to 8 into 1 plus 3 raised to 7 into 2 plus 3 raised to 6 into 1, 3 raised to 5 into 1, blah blah blah. Right? So what?
I'm not sure if I have a solution, but
Mhm.
I would like to try. Since we know that n can be expressed in base k, then
Yeah.
someone will have to win. Someone will
Mhm.
have to win. The game has to win.
Yes, that's for sure.
Yeah. So if for k is equal to 3, if k is 0 and it's your turn, then you lose. Correct?
No, k is not changing. N is 0 and it's
So
your
if n
turn,
is
you
equal,
lose.
yeah.
Yes.
But if n is 1, then you can subtract 1 from it, and then
Yes.
Alice will
So
have.
actually, yeah, let's write down, right? 0 is it well
N.
defined?
It's
Let's
n,
just
right?
define from 1 onwards, just for the sake of 1 is p, right?
P. But
Yeah.
2 is
Let's just
P
write 0
because
is also there. And
but
2
2 is
is
N because it sends you to 1 and N is P. That's the only
right.
option.
Yeah.
But 3 is P because he can directly send you to 0.
You can also go to 2, by the way, which is n.
Yeah, so all options are N, so we are guaranteed going to win.
Yes.
Yeah.
Like even if you make a random move, you will. Okay.
Okay, so
What about 4?
for 4 we can
Okay,
just
also for people who may not be following as quickly, also, yeah, just to answer one thing on chat, yeah, the issue with trying to do something which is like base k, which is like count the sum of digits in base k, is carry forwards and this thing. So like I can actually subtract from here. Who is stopping me from doing that? Like it's not this will not become -1. It'll just become there'll be a carry forward and this will become 2 and this will become 0. So it's not actually that simple to do base k, and in fact it doesn't really work very well, which is a very intuitive thing for this problem. I agree, and that's what I also first thought, but it didn't work. In fact, the solution doesn't have much to do with sum of digits in base k. But okay, yes, coming back, we'll just quickly go through what we've been doing, just so that it's a little slower for people who might have been struggling. Like the point is, 1 is definitely a p position because I take out 1 and I win because now he can't make any move. 0 is an n position because whoever has to play now can't make any move. 2 is an n position because my option is to go to 1. That's my only option, in fact. And um, and like it's a P position, and it's not N. So now the next guy is going to win. So it's N, and then we keep doing this. So like three, your options are 2 and 0, and both of them are N. In fact, you just need one of them to be N. So 3 is a P position. Similarly, 4 is an N1 because 4, your options are what? You can either go to 3 or
Or
you
you can
can
go
go
to
to
1.
1. And both of them are P. You need something to be N, but none of them are N. So this is N.
We can go in 5, we can go to 2, so that is P.
You don't even need to go so far. Just go to 4.
Yeah.
Yeah.
Or
So
maybe
4.
at
In fact,
6,
again, like again, 5, whatever you do, you seem to be winning. So what we seem to be getting, in fact, is like your destiny is pre-decided. It does not really matter on the move you're making, which is really funny.
yeah.
Um, but that's only for small numbers. We don't know if that generalizes for big ones.
At 6,
Uh,
it is N because the only moves are P, 5 and 3, which are both P. 7
mhm.
can send you to 6. 8, our only options are 7 and 5, both P, so it's N. So we can continue this, I'm sure, and then it will be alternating of P and N.
Yeah, that's the question, right? How are you so sure that you can continue this very nicely?
No,
Because
well,
like one part of it is very simple because if you know that n minus 1 is n, then you can very easily say that n is p because I can subtract 1, right? And I can go to an n position, so n becomes p. But the question is if n minus 1 is p, then why am I sure that n is n? Because like now I have a lot of options. I have n minus 1. I can also go to n minus 3. I can also go to n minus 9. I can also go to n minus 243 if n is big enough. And I have to be sure that all of these are p so that I can be sure that this one is n.
I think I'm not sure if I'm right, but
Mhm.
I've noticed that k to the x, if k is 3, they're always going to be odd. So
Exactly.
I've noticed that. So if all the p's, they're already like all the numbers that are p, they're already odd. Because if
Uh-huh.
we subtract an odd from an odd, we get an even. Then the
Yes.
second player has to subtract an odd from the even to make it odd. Then you
Yes. Yeah.
can keep on going like that.
Yes,
So
that's
is
the main
that
idea.
it?
So
Or
basically, the idea is like if you have some odd number, now whatever move you make to it, it'll become even. And if you start with an even number, whatever move you make to it, it'll become odd because you're always subtracting an odd number. Then you're using basic things like odd plus odd is even. Don't ask me to explain that now, please. I don't think I know how to prove it. But yeah, so that's the basic idea that if you have that's why actually the game is actually pre-decided. So if you start at an odd number, then the parity is going to keep switching every turn. So at this, whenever it's one person's turn, it'll always be odd at the end of your turn, which means that at the end of my turn, the answer is never one or something. So basically, um, okay, how can we formalize this? It's like basically saying that okay, actually, we can easily formalize it even like this because the idea is that n minus 1, if n minus 1 is odd, then n minus 3 is also odd, n minus 9 is also odd, n minus 243 is also odd. All of these are odd numbers. And we know that the answer for all odd numbers is what?
yeah,
P.
it's P.
So
And
we can induct using that.
sir, I think
Hmm.
that in these P numbers, no matter how hard you try to lose, you'll end up winning only because
Yes,
you're guaranteed
exactly.
to win whatever you do.
Exactly.
Don't
Exactly.
it?
Because this odd
Uh,
and even has to switch. You cannot prevent it from switching.
yeah,
Yeah. And
whatever
that's very cool.
ends,
But a
there are
very,
only
very
n
big
levels
thing.
too.
Hmm.
All the levels that can be sent are only n. So that's why
Yes.
you have to win. You
Yes.
you
And
need
the
to make it.
very cool thing is like you have like an infinite set, but all of them are odd. That was really what governed everything. What happens if case 2? Now you have 1, 2, 4, 8, blah blah. So almost everything is even, but we have an odd as well. So now things are a lot messier. So I hope that part is clear by the way. 1, 3, 9, 27, 81. If all of your possibilities are odd, then basically the parity of n has to switch on every turn, and so the winner is predefined. Basically, whoever started, if you started an odd, then on your turn it'll always be odd, so you can't lose because it'll never be zero on your turn, right? Because if it was zero on your turn, that's the only way you lose, but that's not happening. So if it's odd at the start, so if n is odd, then you're guaranteed to win, and if n is even, you're guaranteed to lose. But the issue now we're saying is, what if case two, or in particular case even, because then you would have one, and then you would have lots of even possibilities. So you can now control this a little more because you can make it go from odd to odd. You can also make it go from odd to even. It's a lot messier. But this is good progress. We have solved the problem for half of k. Like not half of k, but half of the possible values of k. And yeah, now is the remaining half. How do we go about doing such a thing? So let's actually just, bash out some stuff again. Because like when in doubt in combi game problems, just list down the first 10 answers and I guarantee you will see some pattern and you will have some progress. And then you'll have some way of, okay, this is a good place to start. So 0 is again n, 1 is p, 2. Also, people who haven't been talking a lot, um like if you talk, it's good for all of us, I think. Hello.
Sir, I think that
Mhm.
I think 2 is winning because is P because we can just send it to 0.
Exactly. Yeah, that's easy.
And
What about 3?
it's N because 2 and 1 are P.
Mm-hmm.
And
So yeah, both of your
4,
possibilities are P, so this is N.
so basically in general k raised to if n is equal capital N is equal to k raised to x, then it is going to be P only because we can just subtract from k
Yeah,
raised to. So
yeah.
4
So
is
this also
P, 8
P.
is P, 16 is P, and so on.
Sure.
5 is
Yeah,
going to
let's
be
just. Hmm.
5 is going to be N because all. So we can prove that k raised to x plus 1 is always
Are
going
you
to be
sure?
N.
5 and 3.
Yeah, I think. Oh, okay. 5 and 3. Okay. So 5 and it's P. Then 6 is going to
Yeah.
be I think no. Oh, all are P, so we are going to be losing. It's N. For 7,
Okay, actually, let's stop. Let's see the pattern. Any pattern visible? Like quite directly.
yeah, so for
I
after
think it's
for every 3
NPP.
ones, we're getting an N. For every
Hmm.
3.
Yeah. I think what both of you are trying to say is that for numbers divisible by 3, you're getting N, and others you're getting P. Now,
Yeah.
proving this also, by the way, takes a little bit of number theory. I'm not sure exactly how much I can assume. I don't know. Maybe I should have chosen not to do this, but it's actually not anything very fancy. We can probably do it. Um, yeah. So the question is basically that if I have uh, 3k plus 1, then I can subtract 1. So I can make it n. So 3k plus 1 will be p if 3k was n. And then 3k plus 2 also I can subtract 2 and I can make it p. Make it n. So again it's p. Right? This is fine. The question is, why should 3k plus 3 be n? Like if we
Because it
can
is
do this,
divisible
then
by
the
3.
induction is complete.
Because it is divisible by 3.
Yeah, that's what we want to prove. We want to prove that if
Yes.
3k was n, then 3k plus 3 is also n. That's the induction to show that all
Yeah,
numbers
so
divisible by 3 are.
by induction, all numbers divisible by 3 are n.
For smaller.
And all of 3k plus 1 and all of 3k plus 2 is p only.
Yeah.
What about in general when k is some other number like 3 or 4? Then
Yes, that's what we'll solve the more general this thing.
then it should
But
be then k into k plus 1, I guess.
no, it's actually a little weird, and we'll see what exactly it is. But for now, we've still not done this, right? 3k plus 3, how do we know is n? Based on the fact that we know that only multiples of 3 and 0 to 3k are n. So essentially, if 3k plus, okay, let's assume that 3k plus 3 is, for the sake of contradiction, p, right? That means that you can go from 3k plus 3 to somewhere which we know is n, right? That's why something would be p. If you can go to something which is n, right? And we know that only things that are n are things divisible by 3 for smaller things. Oh no, I think I chose some text thing. That was not a good idea. Okay, so something like 3k or 3k minus 3 or something. And
Understood.
yeah, the issue
Understood.
is,
Yeah, we cannot reach to another number divisible by 3 by power of 2. The number,
exactly,
you have to subtract a number that is divisible by 3 only. But
yeah,
3n is cannot be a power of 2. So it has to be n only. And therefore by
yeah,
induction, all numbers divisible by 3 are n only.
yeah.
It can't be p.
Yeah, that finishes our induction. And we're basically going to be doing these sorts of strong inductions a lot. And like basically assuming that everything till here worked out nicely, and why does this also work out nicely? So yeah, for 2 also we are done. But what about something like 4? Actually won't give away the full thing. I think that's something for you also to work. I'll if you want a hint or something, you can always ask me on Discord or something, and um, or yeah, probably something like that. But I think we've gone a lot of into this problem. There were a few other things also I wanted to do in this class. So yeah, there is. It's actually very cool as to like it's not what you expect. For example, if k is 4, you might think that it's all numbers divisible by 5 or something, but it's not just that. In fact, those work, but there are also other numbers that work. So it's quite cool as to what exactly the pattern is. And this actually came in a coding competition. So they asked you to prove that um, A and B, like they asked you to print out the winner for the given n comma k. And like what happens realistically is most people just print out the pattern, see the pattern, and then prove the generalized thing. Like they don't, in fact, prove it. They just see the pattern and they guess that hopefully it's provable, which is kind of sad. But yeah, actually, the proof is quite cool as to how these things work out with nice sort of inductions. Okay, now what we're going to be looking at is a technique I'm sure most of you have heard of at some point in life, which is proof by contradiction. But we're going to see how it's very useful in these sorts of combinatorial games. Proof by contradiction. Can someone tell me what this is in general?
Sir, can I say please?
Yeah, go ahead.
Yeah, proof of by contradiction is supposing like there is a theorem and then we want to prove it. So we should assume that the theorem is not true, and then we should make a contradiction, and
Yes,
so
exactly.
that proves that the theorem is true, in fact true.
Yes. So what we're going to do here is, let's say we want to prove that A has a winning strategy. Okay. What we're going to do is assume for the sake of contradiction
A
that
does not have a winning strategy.
exactly that B has a winning strategy
Yeah,
and use that to create some sort of contradiction. Like we're going to show that if B has a winning strategy, then B can't have a winning strategy. Something like that. That's like some sort of contradiction we would have. So it'll be a lot more clear with the couple of problems. So um, yeah, I don't know if I have this problem written somewhere. Actually, Yeah, how familiar are people with chess? Like, I don't need anything fancy. I just need you to know how pieces move.
Yeah, sir, I know very well about chess.
Okay, cool. But like anyone who prefers a non-chess game, because like I'm open, I have quite a few problems and we don't have that much time, so we can choose any. And also, like this is not chess at all. It's just like uses the rules of chess, but like it has nothing to do with chess as such. Okay, anyway, too late. We have a chess problem. Okay, consider the following variant of chess. On your turn, you're allowed to make two moves instead of one. And okay, I've not clarified very well, but the opponent also is allowed to make two moves instead of one on their turn. And again, players alternate, pieces move the same way, and white goes first, so that white can always win or draw.
Oh,
Okay,
I
so
solved it. Can I tell the
it
solution?
No, because I think you know.
Yeah, you told me, I remember.
Yeah. Um. Okay, so like the problem, I'll just clarify again. Like basically, you have like normal chess or something. Like you're allowed to make two moves. So like you can move your pawn, and then you can also move out the bishop or something. Or you can also move your knight or make two moves, and then your opponent gets two moves. So they can move out a pawn, and then they can bring out their queen again together. And then
the answer to
it's
the bishop.
actually not very well defined how you would checkmate in this game because like it's a bit weird. I think what you can say is like if you capture the king, it's checkmate. Like that's a slightly different thing. Because the thing is, if you have two moves, then things in normal chess that may have been checkmate may not be checkmate anymore because your king can make two steps and run away. So it's a bit weird, but like let's just go with it because it's not going to have anything actually to do with chess. Um, it's actually just a math problem, which is disguised. And we're going to use this sort of proof by contradiction. So, okay, first of all, what does proof of by contradiction say? Let's say that black has a winning strategy, right? Let's say black uh, has a winning strategy, which basically means that no matter what white does, black wins. Black has some way to win, essentially. Now, what is the contradiction? That's the main point of all of this. And that's actually very cool and not non-trivial to come up with. I don't know if I made more than 8 or less than 8 or whatever. But yeah. And okay, as a hint, please don't start thinking about scholars mate and all of those things. They're absolutely irrelevant. In fact, you don't need to know how more than 80% of the pieces move. I'll have to calculate the percentage. Now. How many pieces are there in a chess game? Five, six pieces, right? So, okay.
Yeah,
Yeah,
I
you don't
started
need to
thinking
know
of
how
scholars
83
made when
of
I
it.
saw.
Uh-huh.
Remember? I started
What?
thinking of scholars made when I saw the problem.
Yeah,
Remember?
yeah, yeah. Even I thought of it. Like it's a very natural thing if you're good at chess or something. Like think about how you can actually make. Also, yeah, Kian, go ahead.
I think that white can never lose only because he's able to move first. If black moves first, then he'll always win or draw
Yes, exactly.
because of the
Like,
symmetry of the chess pieces, and they both
yeah,
have the same rules.
yeah. Like the point is that we want to show that the first player can always win or draw. White and black was just like white and black you can imagine as Alice and Bob, not.
If black could go first, then black will surely win or
Yes,
draw. Only
yes.
because white has the first move advantage, he can win.
And
He can never
actually,
lose.
that's actually very close to what we're going to do. But what is happening is, we have assumed for the sake of contradiction that black has a winning strategy. So you're saying that, your first move advantage was not really an advantage, it was a saddening thing. Like because you moved first, you lost. So is there some way to make black start in something? I think I gave away too much, but yeah, Kian, I think you want to say something more?
What
Or,
if
hmm?
what if what if you want to make black go first, because it can always be a draw because of repetition, but you can just keep on moving the same piece twice.
Yeah, same piece, but like, what if I just move like a pawn twice? What do you mean? Something like that?
Okay, let's say you move a knight and then you move the
Exactly.
knight back.
Yes. That
Yeah,
is the solution, in fact. So you move your knight
yeah,
out, then you move the knight back in. And if
Uh-huh.
black had a winning strategy, now it's as if you are black and you can use that strategy against them and you can win. So it's a contradiction. So they couldn't have had a strategy in the first place. Yeah, realistically, this is not going to be the ideal move. Like, there might be a better strategy to actually force a win, but I can use this strategy to prove that black cannot have a winning strategy. I have not actually shown that this is the best move, and most probably it's not a good move at all because now you're almost uh, like now you're guaranteed to not win. You're just hoping for a draw. But um, what I've shown is that if the other player had a winning strategy, now I can use their strategy against them and I can win. So they can't have had a winning strategy in the first place, and that's a proof by contradiction. So yeah, and I think this is like really cool because like you don't expect that you want to give away that advantage because like the problem kind of gives you this advantage of starting and you're giving it away to the other person because if they had some very good way of using it, now you can use that against them. So yeah, I think it's a very cool idea that comes up actually in a lot of problems. In fact, we'll do one last problem for today and then we'll wrap up. Um, okay, I think we can do this. This is actually I'm not 100% sure if you're allowed. Pranav, would it be an issue if I do the MBL application problem? MBL applications are over, right? Like they can't be
Yeah,
done.
and they change the problems everywhere, so you can't do it.
Okay, cool. Fine. Yeah,
If you can
this
use it
is
in like
from.
the Sophie piece, then why not?
Yeah, I mean, Sophie's still private. Like you don't know. Like you can still get away with it.
You do
Okay.
realize
Anyways,
that this is going to YouTube.
yeah, but it's fine. I think they do change it every year. That is true. So okay,
Yeah,
one, two,
last year we
three.
did a problem in the class from last year's application, so it's fine.
Okay, cool. So 1 to 3 up to n are written on a board. And what you're allowed to do is you're going to pick any, let's say, I don't know, you pick 6 and you cross 6 out, but you also have to cross all of the factors of 6. So like 3 is a factor of 6, 2 is a factor of 6, 1 is a factor of 6. So you have to cross all of these out. And now what is left is 4, 5, 7, all the way till n. And then now the other person plays and they choose some n. Let's say they pick 8. And now they cross out all the factors of 8 that are still on the board. So for example, 4 is still on the board, so 4 also goes. But 1 and 2 are already gone, so you don't kick them out again. They're gone. And then someone, I don't know, kicks out 5. And five's only factor is 1, and that's already gone. So that's fine. And you keep doing this. And if you remove the last number, you win.
What if you, because Alice goes first, what if you take off all the composite numbers, like all the like the large composite numbers, then you
Yeah,
can
but
get
you're
many
only allowed to
factors
take out
at
one
once.
number and all of its factors on your turn. You can't take out lot of numbers, like lot of numbers with all their factors.
No, like one number, but with like many factors, like a
So
composite
like,
number with
let's say
many
1, 2,
factors.
3, 4, right? Let's say I choose 4 because it has the most factors here and I get rid of 4, 2, 1. And then Bob will take out 3 and they will win. So that's not very good, huh? So I don't necessarily want to remove as many numbers as possible. I just want to remove the right number of numbers. Okay, also let's just convince ourselves. The question says show that Alice has winning strategy for every n. So for example, for 1, you just take out 1. So there Alice wins. If you have 1 comma 2, I take out 2 and along with that 1 also counts. So again Alice wins. 1, 2, 3. This is slightly harder. What do you do here?
Alice will have to erase one, and then Bob will pick
Exactly.
either 2 or 3, and then Alice can erase the other one and win.
Yeah. So again Alice wins. What about 1, 2, 3, 4, which we were doing here?
Alice will have to erase 2, and then Bob will erase 4 or 3, and then Alice will erase the remaining number and will win.
Yeah. Cool. So yeah, there does seem to be a strategy for each end, but it's not very easy to describe because like sometimes you were deleting 2, sometimes you were deleting 1, sometimes you were deleting something else. And like the basic idea that we were getting at each time is you get an even number of co-prime numbers left. And then you can basically, each turn is basically just kicking out one number, at which point it's very easy to figure out what happens. But it's not actually that easy for very big end. Like if you're 1 to 100, it's very hard to predict how this game is actually going to go. But even without finding the strategy, somewhat similar to double chess, where I didn't find the strategy, but I proved that there can't be a strategy for the other player. So that's what I'm going to do again. I'll say that, like, uh, let's assume for the sake of contradiction that Bob has a winning strategy. And general thing that is quite well known is like FTSOC, for the sake of contradiction. Bob has a winning strategy, and we want to somehow use this to contradict ourselves. And I think this is a very cool problem, and it's like once you solve it, it feels very easy, but it's actually not easy at all. So I don't think I want to give away the solution actually. So maybe what I'll do is you people can think about this now. Again, if you have some question or you want the solution, you can always ping me or something. Um, yeah, I think I'll leave it at this. The solution is actually a one line thing. Um, and but it's quite hard. Uh, yeah. And it's especially hard when someone doesn't tell you that you have to do this. Because, like, you can always try to do that P and N thing. And, like, it's actually very confusing. How are you even defining your P and N positions? Are you defining it using sets? Because if you have, like, now all possible positions are all possible subsets of 1 to N. Not all possible, but most possible. Something like that. And you want to show that no matter what happens. And I think the common theme in these problems, I'll just give a hint, is that you want to use something that ends up happening anyway. That's a bit of a cryptic hint, but once you solve the problem, you'll really know what I was talking about. And yeah, that's your hint. Like, um, once you want to use to your advantage a move that was going to happen anyway. And I guess I'll leave it. Or maybe I'll give the solution off. Or should I?
Oh, by the way, also you might want to add like in such a games like finding the winning strategy always does not work. Like you can just
Yes.
finish off the question without finding it explicitly.
Yes, like this is a very special sort of problems where you've not found any strategy at all. This is what I said earlier too. And you're only showing that the other person can't have a winning strategy. So I do have it. I don't know how to find it. So that doesn't make it a lot. I can always flex on the other person that hey, I know I can beat you. I just don't know how to. So, not very useful, huh? But for a math Olympiad problem, it's really useful because, like, they just ask you to show that it exists. They don't ask you to find it. Sometimes they ask you to find it, in which case you would be doomed. But here they didn't. So, yeah. I think I'm mostly done with what I had planned today. Any questions, people? Anything that you feel was unclear, you want to ask again? Else we can, I think, stop recording. Okay, some questions in chat. Uh, yeah.
Yeah, okay, I'll stop recording then.
Okay, cool.
Oh, you have to stop recording. You are the host.
Oh, okay. I'll stop. Are you